Hi, everyone. Thank you for joining us. My name is Phil Liu, coming to you virtually from the National Conservation Training Center in Shepherdstown, West Virginia. And we will be giving a webinar today on developing divergent, plausible, and relevant climate futures for near and long-term resource planning. So without further ado, I will have Abby Lynch introduce our presenter.
Great, thanks, Phil. Hi, I'm Abby Lynch. I'm a research fish biologist with the National Climate Adaptation Science Center, and it's my pleasure today to introduce Dr. David Lawrence, who specializes in aquatic ecology and has worked as a climate change scientist within the National Park Service Climate Change Response Program since 2017. In this role, David conducts and translates climate change research to support forward-looking land and water management. Thanks for joining us today, Dave.
Thanks for that introduction, Abby. Well, thank you everyone for joining. I'd just like to start by acknowledging the folks that helped me with this work. That includes Amber Runyon, John Gross, and Gregor Skierman from the National Park Service, as well as Brian Miller with the USGS North Central Climate Adaptation Science Center. Okay, just to set the context here for this talk, Bill Monahan and Nick Fisichella back in 2014 published a paper on historical warming within the National Park Service. The figure on the left demonstrates essentially those parks that have already experienced significant warming. These are considered extreme warm in the sense that their recent climate observations are greater than essentially 95% of their historical conditions. And those historical defined as essentially the past century. We refer to this map often as the measles map of the Park Service. And it just demonstrates that climate change is here and now, and it's already affecting many parks across the service. And we expect that that warming will continue, and that impacts to the resources that we are engaged to protect will occur as a result of this warming. This has been picked up quite a bit in popular press, and there's just a couple examples here. The one on the left from the National Geographic stating basically that America's most special places will always be beautiful, but a warming climate forces us to accept that they cannot be frozen in time. I think that states it well. And the cover on the right is from the New York Times, and this is a more recent article that puts forth this question, what to save? Climate change forces brutal choices at national parks. And indeed, we are facing difficult choices, and as a result of climate change within the Park Service. In relation to the change that we're experiencing and really the mission of the program that I'm within, which is the Climate Change Response Program of the Park Service, we're really trying to be intentional about planning for climate change as we proceed into this sort of uncertain future. Part of that has been developing the guidance that you see on the right called Planning for a Changing Climate. And this guidance was released last year, and it builds on the Climate Smart planning guidance that was previously released, but is sort of adapted specifically for the Park Service. I just wanted to point out a couple of the fundamentals that are specific here and that will resonate throughout this talk related to adaptation planning. The first being that we need to develop forward-looking goals that consider the future climatic conditions, and that when we're planning, we need to consider more than one scenario of the future. And I'll describe what that means as I go here. So in this context of planning and in an uncertain time, traditional planning basically assumes that the future looks like the past. In doing so, we tend to be overconfident in our ability to predict the future. We think narrowly, and as a result, we may leave ourselves open to surprises. This is contrasted by scenario planning, which is not based on the past, but really looks forward and thinks about what could happen in the future. And scenario planning is particularly valuable in these situations of irreducible uncertainty, like the context of climate change. Scenario plans generally ask what might happen and do so in a rigorous and creative way. The idea is to think broadly, be open-minded, think through all the different possibilities, and as a result, proactively plan by how we might change how we plan to these in response to these different futures. And characteristics of scenarios that we use in scenario planning are plausibility. So the scenarios have to be science-based and plausible. Divergent, meaning we want to think through very different ways in which climate change may affect a particular place or resource. And that's the diagram on the right implies. Relevant, meaning relevant to the resources of the decision context that we're trying to inform. And challenging to entrenched mindsets. That is to denote this idea that we want to think in a very open-minded way the different changes that may occur and try to prevent ourselves from being totally surprised. So scenarios, in a sense, are a way of dress rehearsing for the future. And the organizations that conduct this kind of work, they can have various benefits, including quicker reactions to a changing world. You've already sort of played out some of these changes and thought it through. You can develop more flexible plans because you've thought about the way different futures may play out, create innovative ideas. And then one that I think that's particularly important is have early and broad risk identification. The Park Service itself has been engaged in scenario planning since 2007 through a variety of participatory workshops, including 90 plus parks, regions, and networks, and a variety of partner organizations have been engaged in these scenario planning processes. Really an early and essential step to developing plausible scenarios is to generate climate futures. And so first I'll define what a climate future is, because I'll be using that word quite a bit in this talk. So a climate future is a description of the physical attributes of climate that can plausibly occur in a specific time and place in the future. And so useful climate futures, they focus on climate metrics that are relevant to a specific resource or decision. And we typically use multiple climate futures to consider the range in which climate may change. And we'll see that as I move forward here. Just to give you a few examples of what a climate future may look like. This is just a figure showing change through time in mean annual temperature for Timpanogos Cave, which is a park in the Park Service in Utah, and the historical temperature being in the gray. And then we're contrasting here a warm, wet climate future with a hot, dry climate future. And then another climate metric that may be relevant for this particular park may include climatic water deficit. And so again, we're showing the historical in gray and that water deficit under a warm, wet climate future in blue and a hot, dry climate future in red. So climate futures are really designed in part to characterize uncertainty. And we want them, divergent climate futures will describe the broadest range of the futures we may experience. And the divergent climate futures can support decision makers by allowing them to understand the range or the spectrum of change that the resources may experience. We can develop strategies that are robust to a range in that change. And then the goal is to also avoid highly consequential surprises. And just to give another example of climate futures, here I'm showing the Grand Canyon landscape with the Grand Canyon itself in that black polygon, and then the Kaibab Plateau lit up, showing the number of days per year when the snow water equivalent is greater than 0. So essentially this is snow days, and that's the historical condition. And then here are different climate futures for how the delivery of snow may change in this landscape. Climate future 1 on the left under mid-century and late century, climate future 2 on the right, and this is contrasting a warm, wet climate future under climate future 1 and a hot, dry climate future under climate future 2. And in this case, the projections of snow are really relevant to the Grand Canyon, because Roaring Spring, which is essentially the sole water supply for the Grand Canyon South Rim, basically relies on recharge from snowmelt on the Kaibab Plateau. And so these kind of changes will have really significant influence on the park. Translate climate futures into climate resource scenarios. So if you recall, the climate future is that physical attributes of climate, and then the climate resource scenario takes those and identifies the potential resource implications of that climate future. And this is generally done in collaboration with managers and resource specialists. And so the figure on the bottom there is just kind of a cartoon of what what these two pieces look like. And of course, we're generating multiple climate futures and multiple climate scenarios, and that's just a reminder there. Ultimately, we take those scenarios and we use them in decision making, and the goal is to use them to develop adaptation strategies and use these scenarios to inform management decisions and feed them into the various planning processes that the Park Service engages in. So here I'm just showing an outline of the various pieces of what I'm going to be talking about, and there's a bunch of them, so thought it might help us stay oriented and on task. So I'm going to start by introducing Big Bend National Park as a kind of case study or example of developing climate futures for a water management planning issue there. And using Big Bend as this case study, we'll describe 3 different approaches to generate divergent climate futures that we can feed into a scenario planning process. And the first is RCP-based ensembles, the second being quadrant-average approach, the quadrant-average approach, and the third being the individual projection approach. Then we'll move to comparing the range of uncertainty captured using these different climate future approaches in the 2040s, 2060s, and 2080s. And this is to align with near, mid, and long-term planning efforts, all of which we engage in within the Park Service. And then we'll flip back to explain basically how we use the climate futures from Big Bend to inform this specific water management decision. And then we'll close out with talking about some of the considerations and trade-offs when selecting a climate future approach and some tools to develop climate futures, and then finish with some conclusions. So first, let's talk about Big Bend. So for the Big Bend is in Texas, and if you look to the far right there, it straddles the US-Mexico border and right along the Rio Grande. It's a pretty amazing park that is experiencing some pretty significant warming, and that's demonstrated here by the climate change resource brief. You see basically mean annual temperature that traced through time over the last century. And again, this is some work done by Monahan and Fisichella, basically showing using a variety of different temperature metrics. Basically, this park is in extreme warm condition relative to essentially a century of climate. We expect more warming there. I'll get into that as we proceed, but I want to highlight a particular part of Big Bend National Park, the Chisos Basin. And what you can see in this figure is if you look to the about the center of the figure, you can see some of the infrastructure that's within the Chisos Basin. So it contains a restaurant, a hotel, a store, and some operation buildings for the Park Service there. And it's a really neat area of the park if you ever get a chance to go. And it's one of the most widely visited parts of Big Bend National Park. All of the infrastructure within the park relies on this one shallow groundwater spring called Oak Spring, and this is on the desert floor. And this Oak Spring is fed by precipitation, and it was developed back in the 1950s, and so it's about 7 years old. And the infrastructure and plumbing that essentially delivers water from Oak Spring up into the Chisos Basin developed area, it needs to be replaced. And these are just some more pictures to show. You can see kind of the exposed pipe that wasn't exposed when it was originally installed, but that's essentially the pipe that's moving that water from that shallow groundwater spring along the window trail back up to the Chisos Basin, and you can see it goes into a water storage tank that's pictured on the upper left, and then essentially all the water that's used at the hotel, the restaurants, etc., essentially comes from this one spring. So the park had told us when we initially started discussions about developing some climate information for them that the spring is responsive to contemporary precipitation. And we confirmed that by basically pulling some data. This is a decade of flow data from Oak Spring, with the flow being in the red dots, and the rolling 3-month of precipitation being those blue lines, basically confirming that these precipitation events occur And then we see a lag, and then that we see that expressed in terms of elevated Oak Spring flow. This is important in the sense that some springs may be deriving water from a deeper, much larger aquifer. They may be ultimately fossil water. And so other springs may not really reflect what's happening in terms of contemporary climate. That is not the case here in Oak Spring. We know that based on this data, as well as some other hydrogeology data, that this is responsive to contemporary precip. I circle the 20 gallons per minute of spring flow, and you can see the dotted line that corresponds to that. Primarily just to point out, that's a threshold of management interest. Anytime that flow for Oak Spring drops below that, and you can see that occurs during several periods in that decade record, the park operations get really challenged. So for example, the restaurant may have to switch to disposable cutlery and disposable plates. Water use in general is just diminished, and it also represents challenge in terms of water for fire management within the basin. So Bob Krumenegger, who's the superintendent of Big Bend National Park, and others reached out to us basically seeking some information about climate change in relation to this, to some decisions about how to redevelop Oak Spring as a water supply. And I like this quote on the right. He basically says, we need to understand not what the future will look like, because nobody can predict that, but we do need to understand the range of possible futures. And so this is a pretty classic situation for where we can employ scenario planning. And so the management question they're ultimately asking is for us to assess the risks and benefits of 3 potential actions related to Oak Spring. The first is to redevelop that water supply as is. The second being to redevelop the water supply, but to reconfigure it to withstand longer and more severe dry periods. And the final option being to switch to another water supply that pulls from older, deeper groundwater, one that's less sensitive to contemporary climate, basically. This is not a cost neutral decision. Big differences amongst these options and ranging from 10 to 20 plus $1 million. So this is a big decision. As such, there's a desired longevity for the redevelopment as it occurs. So investigating future climate conditions is really a key part of choosing amongst these different options. So we developed climate futures for the park based on 2 primary axes of uncertainty. The first was the degree of warming that the Chisos Basin may experience. And we were interested in that given its potential to influence evapotranspiration, essentially how much of the precipitation that's delivered may be returned to the atmosphere, as well as the amount of, or the change in precipitation delivered to the basin itself. So some of the specifics about generating climate futures. So I'll start with guiding viewers here to the left, to the figure on the left. If you look at the map in the bottom right of that figure, that shows the polygon boundary of Big Bend National Park with a climate grid overlaid on top of it. And then there's a brown square, and that corresponds to the brown square that's above that map. Essentially, this shows the grid cell at 16 square kilometers that we chose to investigate. And this grid cell was chosen because it corresponds to the recharge area for Oak Spring itself. So we pulled 20 global climate models, or GCMs, from the CMIP-5 archive that were downscaled using the MACA method. Each of these global climate models is driven by the RCP 4.5 or RCP 8.5 climate emission scenarios. Are for 4.5 essentially corresponding to a middle of the road emissions, and the RCP 8.5 corresponding to sort of a high-end business as usual emissions situation. I wanted to define the word projection because I'll be using it a lot. So when I say projection, I mean a climate model that's driven by a specific radiative forcing. So for example, the IPSL model driven by the RCP 4.5 would constitute a projection. So if we take the 20 GCMs and we drive them by 2 different RCPs, we end up with 40 different projections of the future for this recharge area of Big Bend. And then we assess that across 3 different 30-year time periods, the 2040s, 2060s, and 2090s. And then we ultimately compare that to the historical period of 1950 to 1999. Now I'm going to transition to describing the different approaches for generating climate futures in this Big Bend case study. So starting with just describing the projections themselves. So the figure here just shows on the horizontal axis the change in annual mean temperature from the historical condition, and then the vertical axis being the change in total precip under the historical, compared to the historical condition. Again, this is for the Oak Spring recharge area, and these projections are for the 2040s. And the legend on the right just shows which projections correspond to which numbers, but the general point here is that there is uncertainty in terms of these different 40 different projections. What we see is that all the projections indicate that the future will be warmer than the past. They all essentially lie to the right of 0 on the horizontal axis. In terms of the precipitation, I drew a dotted line here through the 0. So that would be no change in precipitation. So if projections are above that line, that would imply increasing total annual precipitation. If projections are below that line, that would imply reductions in total annual precipitation. So the first approach to generate climate futures is to use essentially the representative concentration pathway approach. And most folks are probably familiar with these, but RCPs, they basically reflect this broad range of socioeconomic futures and a range of climate forcings from 2.6 to 8.5, effectively from high to low, or low to high, excuse me. And the RCPs themselves provide this convenient means for building climate futures. And the divergence amongst these RCP-based climate futures really represents uncertainty about greenhouse gas emissions. And so you've already seen the panel, the upper panel, which are the projections in terms of temperature and precipitation space. Those same projections that are essentially denoted or colored by their RCP is the panel below it. So all the blue projections are RCP 4.5, and all the yellow projections are RCP 8.5. Ensembles of the RCPs should basically just involves taking the average of RCP 4.5 in blue, that blue asterisk, and then the yellow asterisk is the RCP 8.5 ensemble or climate future. We can contrast this with the quadrant-average approach to generating climate futures. So to do this, we basically, again, these are the same projections, we're just dividing them up in a different way. So the scatter plot on the bottom, we divide this into quadrants, essentially by first finding the average of all these different projections. That's the center point of those 2 dotted lines coming together. And we excise the central tendency of those 2 axes. So that's the 25th and 75th percentile. And then the subquadrants that surround that box essentially can make up different climate futures. So here I'm highlighting a warm climate future in the upper left, where we experience moderate warming and increasing precipitation in the recharge area for Oak Spring, and then contrasting that with the bottom right, which is a hot, dry quadrant average future. And essentially, for the asterisk represents the average of all those projections within that subquadrant. So essentially, that is what the climate future is under warm, wet, and hot, dry climate futures. And just in relation to the water management question itself, warm, wet would be, a best case scenario, basically, where they would be receiving more precipitation. The hot, dry future would represent a worst case where precipitation is declining and things are getting much hotter. The final approach is the individual projection approach. Again, same projections. Now we're just essentially selecting individual projections to represent different climate futures. So in this case, we're selecting the CNRM model for a warm, wet individual projection and contrasting that with the IPSL model in the bottom right, which is a hot, dry individual projection. So now what we're going to do is compare the range of uncertainty captured according to these different approaches in these 3 different timeframes, essentially looking across the near term, midterm, and long term planning efforts. So the figure on the right is basically what I just showed you, but we're collating those figures now, putting them into one. Just as a reminder, this is the 2040s, so corresponding to a near-term planning environment. And the upper panel shows the RCP-based climate future approach, the middle panel showing that quadrant-average based climate future approach, and then the lower panel showing the individual projection climate future approach. What we can see is if we compare the difference between RCP 4.5 and 8.5 in 2040, there's not much divergence between these two climate futures, just about a 0.2 degrees centigrade difference between the futures, not much difference either in terms of precipitation, about 0.5 millimeters. We contrast that with the quadrants where the warm wet subquadrant is about 0.9 degrees cooler than that hot dry quadrant-based climate feature. And it's wetter, 82.6 millimeters more precipitation received under the warm wet compared to the hot dry climate feature. And then finally, we see even a greater range of that uncertainty in terms of temperature captured using the individual projection approach, about 1.4 degree difference between the CNRM model compared to the IPSL model. And again, also a greater range of the potential change in precipitation captured, about 121 millimeters in the 2040 period. So just the point here is that the individual projections and these quadrant averages capture a much greater range in terms of the uncertainty than RCPs during this 2040 period. And now if you focus on the figure on the right, I'll step through the 2040s, 2060s, and 2080s. First, just to orient folks, the blue dots there are the projections under RCP 4.5, the yellow dots being the projections under RCP 0.5. And then these quadrants as indicated by the dotted lines, we have the warm wet in the upper left and the hot dry in the lower right. And then the individual projections that were selected are those individual according to that individual projection method are selected or circled with a black circle. And so we can just compare the range of uncertainty captured according to these different methods. So start with the individual projection method. So we're just comparing that that model selected in the upper left, the model in the lower right. You can see how that changes through time. 1.4 degree difference in the 2040s, 2.6 in the 2060s, and 5.4 in the 2080s. We can contrast this with the quadrant approach for generating climate futures and the RCP ensemble-based approach. So the difference between quadrant-based climate futures is less so than with the individual projections. And the RCP essentially captures even a smaller range of uncertainty amongst the different climate futures, 0.2 versus 1.4. And those percentages just relate to what percentage of that total 1.4 as the benchmark uncertainty in temperature, for example, here in the 2040s. And we can just populate that for the 2060s and 2080s. Again, what you can see is with the RCP, we're getting a greater range and difference between RCP 4.5 and RCP 8.5 in the 2080s, 1.9 degrees, but it still represents a relatively small proportion of that overall uncertainty that's captured by the quadrant and the individual projection approach. And remember here, what we're trying to do is feed these different climate futures into a scenario planning process in which we want plausible scenarios. So plausibility defined here by that they're science-based, they're the result of global climate models. They're divergent, so they're different from each other and they're relevant to the question at hand. We can look at essentially the same question here in terms of projections of precipitation. Again, we're talking about the Oak Spring recharge area here and compare how the individual projection method relates to the quadrant-based and the RCP-based method for climate futures. So we can see the span of uncertainty increases through time for the individual projection method from 121, 161 to 256 millimeters. If we compare that to the quadrant RCP, based approach again, and really it's more emphasized here in the precipitation. The RCPs themselves, 0.5 versus 8.5, really don't have much difference in terms of the projections of precipitation. So they don't create much divergence or span much of the range of uncertainty. The quadrant average based method does better. It captures about 68% compared to the benchmark of the individual projection method. And then I'll just populate it for the 2060s and 2080s. Again, the deviation amongst the RCPs increasing through time, but still a relatively small amount of the uncertainty range captured relative to the quadrant-based approach or the individual projection-based approach. And this is just a reminder, as much for me as anybody else, that this is feeding into a scenario planning where we want to think across this broad range of uncertainty and develop scenarios related to that broad range. I'm showing essentially the same information as a time series, starting with the comparison of RCP 4.5 and RCP 8.5 in temperature space and precipitation space through time. So you'll notice within the upper panel for temperature that there's not much divergence in terms of RCP 4.5 and 8.5 up until about the 2050s when those climate futures start to diverge. And within the precipitation space, the lower panel, this range of precipitation is small really and does not vary much through time. And that's really the result of averaging wet models and dry models. We compare to the individual projection approach, we can see that the individual projections diverge through time really from where we start in the 2020s all the way out into the 2100s. And in terms of precipitation in the bottom right, each of these projections is variable through time, but interestingly, in this, the warm wet projection in blue is much more variable than the hot dry projection in red. And just to note here that the Park Service and many other agencies are oftentimes asked to develop climate futures and climate scenarios related to near-term planning questions. And so you can see, if we're just looking out to from 2020s to the 2050s, if we use an RCP approach to generating climate futures, whereas we're capturing a much broader range of potential uncertainty using the individual projection approach. And then we can see the same for precipitation, just a compressed range as a result of averaging within the RCP based futures compared to the individual projections. And specific to the water management question within Big Bend, this variability can be really important to, for example, the reliability of a water supply like Oak Spring. So now I'm going to flip back to talk about how we use these climate futures to inform water management decision-making within Big Bend. So if you recall, we take these climate futures, which describe the physical attributes of climate, and we translate them into climate resource scenarios by identifying the resource implications of those futures. And then we ultimately use those to make some adaptation decisions. So doing that for Big Bend, using those climate futures that we just talked about. Here, this is for the 2060s, climate future 1. This is based on the individual projection approach. That's a hot, dry future that has a 5-degree increase in annual temperature and a 31% decline in annual precipitation. We contrast that by the warm, wet climate future, which has a more modest increase in annual temperature, but in contrast to the hot, dry future, has an increase in annual precipitation of about 25%. So we use some modeling, and I won't get into the details of that here, basically to translate the climate information into Oak Spring flows. And unsurprisingly, what we find where the hot, dry situation is a reduced discharge from the spring. And specifically, we find about double the number of months per decade where Oak Spring falls below that critical threshold of 20 gallons per minute. So that's really going to challenge the use of Oak Spring as a water supply under its current condition. And then again, contrasting that with the warm, wet climate resource scenario where the annual precipitation increases, but so does the interannual variability in precipitation. And based on our modeling, we found that the number of months that Oak Spring falls below that critical threshold under the warm-wet scenarios is essentially similar to the historical baseline. And converting that then ultimately into decision-making or adaptation, what the managers of Big Bend have chosen to do ultimately with Oak Spring is to take some measures to enhance the reliability of Oak Spring proactively to the future. So that includes using water more efficiently. So that could be changing the toilets and the shower heads to being more low flow. That includes improving infrastructure of the spring itself. So the pipes that convey that water from Oak Spring up into the Chisos developed area, which currently have a lot of leaks. And then ultimately, the superintendent decided to double the storage capacity of water that will temporarily store Oak Spring water so that it's available in drought periods. And that additional water storage really is a robust decision to both the hot, dry and the warm, wet feature, because even under the warm, wet feature, the variability in precipitation could be a challenge for Oak Spring as a water supply. And so related back to that initial question, which of the three decisions are they going to do? They ultimately decided to redevelop Oak Spring as a water supply, but reconfigure it to withstand these longer and more severe dry periods. So now we're going to move on to talking about some of the key considerations and trade-offs in selecting climate future approaches and describe a little bit about some of the tools that we can use. So just one thing that's important to note when selecting a climate future approach is that it really depends on the decision you're trying to inform and the time that you have available to actually execute the analysis. It's a context dependent ultimately, and really we advocate that it should not be a one size fits all answer. For example, if we're really interested in mitigation, the RCP approach maybe really allow us to distinguish, particularly as we get out into past the 2050s, what the difference of different emissions mitigation approaches and how those will ultimately manifest themselves in terms of climate features and climate metrics. If we have an adaptation emphasis and we're feeding this into scenario planning, then a quadrant or individual projection approach, which generate and capture a lot more of the divergence, may be the right approach. And we typically use for scenario planning, approaches that capture divergence, plausibility, relevancy, and as I mentioned, that challenging to the entrenched mindset concept. For near-term planning, we found and demonstrated here that the individual projection and the quadrant approach capture a broad range of uncertainty and much broader than the RCP approach, particularly in the near term, but we also found that in the long term as well. And then it's important to note, the ease or difficulty of actually employing these approaches. To do a lot of climate analyses within the Park Service, and we're in charge of 400 plus parks. And so this is a real sort of logistical challenge that we face when we're asked to generate climate futures. So our program has been using the quadrant approach as sort of a coarse filter evaluation in more simple planning context and climate futures, and then individual projections for more detailed investigations where we have more time for model choice and evaluation. I just wanted to note some of the various examples of using climate futures for resource management. We've done so within Badlands National Park, and climate futures and ultimately climate scenarios that come out of those have been used within Devil's Tower, Wind Cave National Park, and are currently in use within Wrangell St. Elias National Park on the far right there, the largest park within the National Park Service system. Amber Runyon, who's an ecologist within the climate change response program, has been developing what she calls the reproducible climate futures program. Essentially, this is a really useful tool for producing climate futures The idea here is to essentially develop a streamlined workflow to increase the efficiency in terms of generating climate futures, so really the time that it takes. Also to enhance the reproducibility, so to make these workflows such that they really meet all the standards of reproducible science, and then increasing the accessibility and really the scale, so allowing many partners, parks, and users outside of the Park Service to be able to generate climate futures using this tool. And this is being coded up in R as a package, the RCF package, with a spring 2022 release. And it generates climate futures and calculates thresholds for 30 metrics using the individual and quadrant climate future selection approach. And you can select climate futures based on temperature or precipitation, or both based on a variety of metrics where you can use something like principal component analysis when you're dealing with multivariate climate metrics. And just to note here that there'll be some training on the climate future creation using the RCF package coming in the spring of 2022, and Amber's contact information there is on the bottom right. And there's other resources outside of the Park Service for generating climate futures for use in planning. The Forest Service document on the left, the EPA's document, they have the climate lasso tool for selecting projections. That's the state of California's tool, which is a really nice interface for selecting climate futures to investigate changes in stream flow, snow delivery, wildfire, precipitation, heat, etc. to the state. And I highly recommend checking that one out. And then the Bureau of Reclamation also uses a form of climate future analysis in their basin studies. This is just an example of Hood River on the far right. And so to pull together what I talked about in terms of some conclusions, just to start, these divergent and plausible climate futures, their intent is to support decision makers in their need to investigate this range of potential futures in their decision process and try to avoid surprises. One of the overarching goals of climate futures is to explore this decision relevant uncertainty among the projections of change. A set of divergent, plausible, and relevant climate futures that will ultimately support scenario planning can help identify strategies that work across all the climate futures. We can investigate and identify strategies that won't work under any climate future. And then we can also look at specific high consequence vulnerabilities that may be specific to a subset of scenarios. So not all the vulnerabilities will appear in all of the climate resource scenarios. I demonstrated with the middle part of this presentation that the individual projection and quadrant average approach to generating climate futures captures a broader range of these plausible future conditions compared to that RCP approach, both in the near term and in the long term. But ultimately, the choice of the different approaches to generating climate futures really depends on that application and the available resources that you have. And just a final note here that the Park Service itself has had a lot of success using climate futures in the scenario planning process in a real broad variety of management planning contexts. So I talked here about sort of the infrastructure planning context, but we of course use it in natural resource planning and in cultural resource planning as well. Then I just wanted to highlight a couple of resources. If you're interested in that's the Big Bend specific story, you can Google or YouTube this warming up to adaptation, where Maneker and others at the park talk about this specific question and how they used climate information to inform their decision. And then if you want to dig in further to the details of what I talked about today, that's all put together within this climatic change paper that was published last year. With that, I'd just like to acknowledge a variety of folks that have been involved in sort of the creation and application of climate futures and their use within different planning environments in the Park Service. And then just thank everyone. I really appreciate folks joining today, and just note that that we have a big team of folks that are involved in trying to help parks adapt to climate change, and those individuals. And there's some that aren't represented in this picture. It's a little old, but we are here to help, and we're hoping to just really circulate and some of the information about our approach and learn from others as well. With that, I'm happy to take some questions.
All right, I'm going to start with the questions in the chat, David.
Okay.
We'll start with Steve's question. He asks, can you provide the name of the guidance you mentioned? This was towards the beginning of your talk, Steve. If you want to unmute and ask what the context was for this guidance. I think it was in reference to scenario planning.
I think what he's asking is about the, it's called Planning for a Changing Climate. And that was released last year, and it builds from the initial climate smart conservation planning guidance. So this is something that should be Googleable, but I can also dig up the URL and download it. I think that's what he's referring to.
Moving on to the next question, Melissa asks, how did you choose the individual CFs to use?
So it's a good question, and that's part of the, that is a key question and a key decision really in the process. So it really depends on the management question that's being posed to us. So within the Big Bend water management planning example, we wanted to contrast sort of a best case scenario with a worst case scenario. So we just used two climate futures. The best case being a future where precipitation increased in the region, and temperature, while it increases, it did so modestly. We contrasted that with that hot, dry climate future where we get a lot of warming, and it's really kind of worst case scenario in terms of the total annual precipitation declining in that Oak Spring recharge area. But in other planning contexts, we may choose 3 climate futures or 4 climate futures. And ultimately, what we do is we try to identify what are the key climate metrics to the resource that's being investigated. So for a cultural resource, for example, we may be interested in the contrasting individual projections that are very different in terms of the freeze-thaw events, and that may be really important in terms of how cultural resources are affected by climate change. So we may want to pick one that has a minimal increase in the number of those events, and one that has a very high increase in those events. But oftentimes, particularly within some of those broader scenario planning efforts, where we're working across a broad variety of resources, so natural, cultural, and perhaps including infrastructure, we may be thinking about 5 different or 10 different resource types. And so we end up, the selection of those individual projections becomes more complex. And so some of that we discuss in our paper, and getting into some of that complexity, we can use some of the multivariate analysis like principal component analysis, but ultimately we would need, and we typically employ some expert solicitation in terms of picking amongst those futures, which are the right futures to generate scenarios that can feed into that scenario process, that are plausible, relevant, divergent, and challenging to the question at hand.
The next question is from Michelle, who asks, was model pooling based on performance against weather station data considered? And then she lists some examples: TP at relevant timescales, annual, decadal, seasonal, etc.
Yeah, that's another good question. So basically, we've kind of, and there's some our general guidance at this point in terms of culling of global climate models themselves, we generally don't cull global climate model unless we have some very specific reason where we know a climate model performs very poorly for a given region, in which case we may pull it out. But in general, no, the MACA downscaling method itself, those GCMs that were selected as part of that process, they already went essentially a culling in terms of their ability to reproduce climate within the United States. And so we essentially capitalize on that process already. And there may be good reason to do model culling in other situations, but for the sake of, in many cases, especially for simpler planning contexts, where we have to generate quickly, that model culling can become a model evaluation can become quite a large endeavor. And so it's kind of a project onto itself.
Janet asks if the National Park Service monitoring network is part of the collaboration. She thinks it would be very useful to set up future monitoring to evaluate the management actions that are undertaken based on climate features, even if we have to wait a few decades to see the results.
Yeah, that's a good point, Janet. And we are working with various staff from INM. We've been engaged particularly with folks that such as David Toma, who have done a lot in terms of water balance modeling. And so we've actually expanded our climate futures analysis really to leverage a lot of the water balance work that David and others have done within the inventory and monitoring program. But speaking to the broader question, can you use monitoring to assess which of the particular climate future pathways you're on? I think that's a great idea, and one that I think is important to pursue, because ultimately, as we proceed through this future, we may identify that we're on one particular path. One scenario is really emerging more so than others, and so that may allow us to focus our sort of resources and our effort to a particular scenario, and monitoring is really a key part of that. And so I think the short answer is yes, we're trying to bring together our efforts with INM in that domain.
Thank you, David. The next question is from Ryan. He states, it is almost always best practice to use individual projections to feed into other models, decision models, process models, ecosystem, etc. Extremes are reduced anytime multiple projections are averaged. Do you have an example of when RCP average or quadrant averages were found to be more appropriate?
The short answer is no. I totally agree with Brian that when you're trying to investigate, when you're trying to use models, you use individual projections. There are some folks that will take, that will first essentially run all the models under a given RCP individually and run them through, and then average, opposed to taking the average itself and running it through a model. Do miss those extremes if you were to take that approach of running the average through the model as opposed to the individual projections and then bringing those together into an ensemble. But no, I don't know of any cases where running the average itself through a model is more appropriate.
The last question in the chat is from C. Olson. He asks, do you take the median uncertainty for planning purposes, or do you look at the complete range? And this is in context of your quote, quadrant approach captures broader range of uncertainty.
Okay, so yeah, generally when we're in a scenario planning context, we're really looking at the complete range, and that's because we're trying to think of these different types of futures that may occur, as opposed to trying to look at the more median outcome. And so in general, with the way we've been using climate futures, we do not use them probabilistically in a similar way that RCPs, that are put forth by the IPCC are also they don't have probabilistic estimates associated with them. It's really about investigating the range of potential uncertainty and planning amongst that. There may be specific context where focusing on that the median may be the right thing to do, but that is generally not the approach that we've taken.
We have time for maybe one last question if anyone else has any.
Sure. My name is Orion Richmond. Hey, David, great talk. Kind of two questions real quick. First, just wondering about the RAD framework, the Resist, Adapt, Direct, that I know has been developed in the Park Service and is being looked at a lot in the Fish and Wildlife Service where I'm working. How has that sort of interacted with the work you've done, or how could that be applied?
Yeah, so RAD is essentially a planning framework for managing ecosystem transformation within the Park Service, and essentially it's delineating the options across that spectrum, as you just noted. So from resisting a transformation to accepting a transformation to directing that transformation towards a desirable future condition that's different than the one that you get if you accept. I think climate futures themselves could be used to essentially delineate some of the different potential futures that we may experience. And those different plausible futures can ultimately be part of looking across that RAD framework. So we can look at the different, for example, climate trajectories and say, how might the system be pushed to be different? And so it may go, for example, a boreal forest might be under one climate future, may be pushed towards becoming a temperate forest. It might remain as a boreal forest, or it might be pushed towards becoming a grassland. And so we can use climate projections as part of the analysis approach, kind of the fundamental analysis to understand what are plausible trajectories of the future. And then we on top of that and say, okay, based on those plausible trajectories, where might we want to resist? Where might we want to accept? Where might we want to direct?
And then second question, excited to see the RCF package and that just work being put into making the production of climate futures more efficient. As you mentioned, there's obviously tons of national parks in the country. There's also a lot of national wildlife refuges and other, public lands. And so I'm just wondering how those efforts, might be leveraged even more to help, some of the other public land agencies out there, and whether that work is happening at a DOI level or higher to try to help get those future scenarios out, because I feel like that's a big bottleneck to doing this climate smart planning is, getting good future scenarios that are downscaled to particular places. And so yeah, I mean, it looks great that there are efficiencies being built in. I was just wondering if that's limited to the Park Service or if there's efforts to do that beyond.
Yeah, the RCF package is agnostic to land management. So anybody with a polygon or a point can generate a representative or a reproducible climate future using that package. Because yeah, you're right. There are a lot of different types of lands, and it is difficult to generate these kind of climate futures if you're just coming in to it, starting off. So this has been a process that Amber and others within our program have been developing over 5+ year period, and we're really happy that we're getting to this point now where we're going to have some tools to automate this production so that other, both within the Park Service and outside of the Park Service folks can do so.
No, that's awesome. I think providing some support for interpreting outputs and, for folks picking it up who haven't spent 5 years working on it, I think would be key to sort of making that successful. But thank you so much.
Yeah, couldn't agree more. Yep. The translation is key. Yep. Thank you for your questions.
All right. Thank you so much, David. And thank you all for joining us today.
Yeah, thanks so much.